Hello, I'm here to walk you through a tutorial about cuckoo hashing. This is a project for one of my college computer science courses. The cuckoo hash got its name because of a trait of the European cuckoo. The European cuckoo doesn't build its own nest, it doesn't take care of its young. Instead, it drops its own egg into another, usually smaller songbird's nest. When the larger cuckoo egg hatches, it throws out the current occupants and leaves itself the sole owner of the nest. The parents, not knowing any better, feed and watch and take care of the cuckoo chick all the way to adulthood. This trait of pushing out the current resident is what gives cuckoo hashing its name. In hashing, if you could come up with a perfect hash function and never worry about collisions, life would be easy. But that's not true. And so what defines various hash algorithms is how they handle collisions. In our text and in our class, we learned about probing and chaining. Probing is when you have a collision, you rehash the index and try a new location. What you're effectively doing is walking through the whole hash table, recalculating and rehashing till you find a null location to put your key. Chaining starts with the initial location linked to what's called a bucket. All keys that hash to the same index are put into this bucket. The bucket is effectively just a linked list. Now, Cuckoo restricts each key to a limited number of possible locations, each determined by a different hashing function. For example, if you have two hashing functions, you will find a particular key in one of two places. What's key about a cuckoo hash table is that, unlike the previous two tables of probing and chaining, we actually modify the table. Probing and chaining just tend to add more to an existing table. Cuckoo hashing actually restructures a table and sometimes completely restructures it. This is very similar to BST or binary search trees, where you build a tree, but at times you may have to restructure the tree for efficiency or other reasons. If you want to get a key from a hash table, probing is effectively the same way as putting one in. If you don't find it the first time, you're going to have to engage the rehash algorithm over and over till you find it. If you don't find it, you will have searched the entire table just to discover that fact. Chaining, you just go to the bucket where that hashed key value is and follow it down the linked list till you either reach the end of the list or you find what you're looking for. Again, since Cuckoo restricts where you can put a key by the number of hash functions it uses, you can find out pretty quickly if what you're looking for is there or not there. For example, if you have two hash functions to create your hash array, hash table, it should take you no more than 2 inspections to find it. Cuckoo hashing is rather new. I think the first paper came out in 2001 by these two individuals, a couple of Europeans as I best can tell. Here we have a set of keys and a pre-calculated set of hashes. This is a 2 hash function table. We have tables T1 and T2 to go along with our keys and hashed values. The rules are pretty simple. For example, you take key A, and you put it in location 3 of T1. If there happened to be something there, you would push out the old occupant of location 3 of T1, recalculated it, and put it in table T2 using the second hash key or hash function. So let's begin with letter A. We've placed A in its location of 3 in table T1. You'll notice I've put a vector between the two possible locations where A can reside. This is going to be important as we build our hash table. Patterns will form and you will recognize what's happening easier. We place B, nothing spectacular. We put in C, again, no collisions, but you can already see the table is getting less and less sparse. We put in D, still nothing, but as you can see, key E is going to go into location 3, and that's where A already is, so we can see what happens. When E went into location 3 of table 1, it pushed out A to its secondary location in table 2 using the calculation of the second hash function. Okay, our next one will be F. It will go into location 6, which we can already see is occupied, and we can see what happens again. B is pushed out of location 6 in table T1 and put into location 6 of table T2. Meanwhile, F takes its position in 6. This is similar to pushing something out of the nest. G is going to start to get interesting. It's going to go in 0 of T1, and you can already see it's occupied by D, and something will happen. Okay, G goes in the location of T1. It pushes D out into its secondary location where A was residing, while A got pushed back to where it was originally, and it pushed E back out into a new location. Now I want you to notice the vectors A, E, G, and D. You can already see that there's a rather confined set of places to put new keys should one enter that area, and that's what H is going to do. Now H is trying to go into location 5 of table 1. As you can see by the vectors or the edges between the letters, you've got effectively 5 locations to put 6 keys. This is a problem. What do? They rehash the whole table. They start from the beginning and they invent 2 new hash functions, and they begin to make a new table. By the way, I used a example of Cuckoo hash that uses 2 tables and 2 keys. You don't always need 2 tables. You can do it with 1 table. The only advantage 2 tables really get you, at least as far as the code is concerned, is that you always know which hash key to use or which hash function to use on a key when you have to regenerate. If it's in table 2 and you need to move it to table 1, you use the hash function h1. If it's in table 1 and you need to move it to table 2, you use hash function h2. But we're going to take a quick look at a single table version of this. I've invented some new hash function values and a new table. The vectors show the alternate locations for each one of the keys that is in the hash table. It works basically the same. The only thing you have to do different is that when you have to move a key to its alternate location, you have to figure out which hash function was used to put it there in the first place. That's the advantage. Two tables get you over one. What you're looking at with the single table was something I found in a paper written by the same gentleman who wrote the first paper. It's kind of a simplified version of the Cuckoo hash. It's designed for undergraduates and me. Basic Cuckoo hash questions. How and when does one determine when to rehash the table? There's no rules when you have to actually rehash a table. As long as the table is still allowing you to insert new keys, it's fine. But in these situations of the loops where you just move data around in a circle, you need a way to detect that. And you could use sophisticated means to count where you've been and where you're going. But the most common method is just to have a big loop value, usually something like the max number of keys. There's alternate ways to calculate what a max value for your loop would be, but that's part of the more deeper science of Cuckoo hashes. How do you rehash a table? I really didn't find a direct answer for that, but the answers I did find were rather simple. You just start at the beginning of the table using your new hash functions, generate a new location and put that key in that new location. If it's already occupied, you do a hash calculation on the old occupant to find out where he's going to go next. Eventually you get your way through the whole table, and if you picked your hash functions correctly, you should have a working table again with no loops, endless loops. Let's see, how much storage should be allocated? One of the in the original paper, the authors indicated that a Cuckoo hash uses about the same amount of storage as a binary search tree would. Basically 2 times the number of anticipated keys. Can you make a Cuckoo hash table that has more than 2 hash functions? Yes, you can. You can use 3, 4, and again, there's a lot of science behind this that you can really get involved with. But the idea of keeping it at a minimum makes your lookup time faster when you have to retrieve a key from the table. What are the major distinctions of the Cuckoo hash? Well, it has a constant worst-case lookup time for finding a key in the table equal to the number of hash functions used. If you use 2 hash functions, you take your key that you're interested in, do a hash with the first hash function, see if it's there. If it's not, you do another hash with the second hash function and see if it's at that second location. If it's not there, you know for sure, because of the way hash or Cuckoo hash tables are designed, is just not in the table. This predictable time from is necessary for some applications. Let's see. Updates. Because every now and then you're going to run into one of these closed loops that causes you to rehash the whole table, there's some basic science says that if your hash functions were reasonably random in their behavior, there is a predictable amount of time that you will spend updating your tables and inserting new keys. Storage use, I guess I did this twice, is the same as a binary search tree according to the authors, about